Namaste. Here I am going to talk about our ISRO's manned mission Gaganyan. Humans are always fascinated. It is their nature to discover new worlds, test the limits of our scientific and technical capabilities, and then push even further. Over the centuries, humans have explored and pushed the boundaries of knowledge to benefit our society. Questioning about our existence in universe, from learning and exploring solar system to outer world of space, human civilization has become a far way to build great tech of not just transportation on earth but also to go on a journey to space on life supporting missions. And we, the Indian Space Agency ISRO, have made remarkable achievements in the space sector with small budget and different focus compared to other countries. India quickly became a global player in the space scene, having attained self reliance in space science, technology, and applications. From very critical attempts such as sending 104 satellites in a single mission to inserting a spacecraft in Martian orbit in their first attempt made India more popular. Next up for ISRO is the ambitious Gaganyan mission, India's first crewed space program. We will study the details of Gaganyan mission and what ISRO hopes to achieve in the future in this particular talk. Human Space Flight Center is the dedicated center who is responsible for implementing the Gaganyan project involving the end-to-end mission planning, development of engineering systems for crew survival in space, crew selection and training, and pursuing activities for sustained human space flight missions. Before we head to the next topic, let us know about different crew members. So, first is astronaut. An astronaut is a person trained, equipped, and deployed by a human space flight program to serve as a commander or crew member aboard a spacecraft. Cosmonaut. A cosmonaut is an astronaut from the former Soviet Union. A taikonaut is an astronaut from China. Now, next, that is our Indian astronaut that is named as Vyomanaut. A Vyomanaut is an astronaut from India. So, moving ahead to mission details of Gaganyan. So, the vision of Gaganyan is to implement a sustained and affordable human and robotic program to explore the solar system and beyond. And we know that as of now, US, Russia, Europe, these countries have sent humans on mission and also did robotic experiments with taking small yet successful steps. India now plans to implement these missions as well. Beginning from low Earth orbit, also the technology of return from space, next main vision is to extend human presence across the solar system. Next important of all the mission plan is to have set up objectives to make sure how the mission has to happen and what are its purpose. So aim is to demonstrate human space flight capability to low Earth orbit with 3 crew members in orbit for 5 to 7 days and safely recover them after the mission. Second, GSLV Mark III launch vehicle carrying spacecraft into a 400-kilometer altitude low Earth orbit for 7 days. Spacecraft consists of a crew module where the astronauts stay, and a service module that contains a variety of support system along with 2 liquid propellants engines to propel the spacecraft itself. These 2 modules combined will make up the orbital module, providing life support for the crew for 7 days, after which they splash down in the ocean. So this is the complete Gaganyan mission profile. As we can see here, according to the objectives mentioned, mission starts from Sriharikota by GSLV Mark III as launch vehicle, taking the spacecraft to 400-kilometer altitude of low Earth orbit. At this point, it stays for a week, then module takes re-entry phase, falling down into ocean or sea with help of parachute deployment for safe landing. Since Gaganyan is the mission to take astronauts to space, it's in its first phase. Test pilots from Indian Air Force were selected from many applicants after detailed evaluation of their health, physiological, and psychological fitness for undergoing training. The test pilots are chosen because of their experience in flying the first or new set of aircraft. Most of the system, like the space where astronauts are going to stay. The communication to the mission control, handling of the spacecraft itself, and checking the progress of their mission are slightly similar to aircraft. Generic flight training for the crew trainees are completed at Gagarin Cosmonaut Training Center. The mission specific crew training is in progress in India. GSLV Mark III is the most suitable Indian made rocket to date. Unlike other GSLV version, Mark III contains only two boosters that use solid propellants type. Mark III is very special because of its unique characteristics. Boosters for the first stage uses solid propellant, that is STPB, hydroxyl terminated polybutadiene, whereas the second stage is powered with two Vikas engines that use combination of unsymmetrical dimethyl hydrogen plus N2O4. The uppermost last stage uses an upgraded C20 cryogenic engine that works with the liquefied oxygen and hydrogen. GSLV Mark III can launch 10-ton category of satellites to low Earth orbit and 4-ton category satellites to geostationary orbit. Moreover, GSLV Mark III is the first human operational rated launch vehicle developed by ISRO. Mark III was used for launch of GSAT 19, uh, uh, GSAT 29, and Chandrayaan 2 and CARE missions. Chandrayaan 2 is the heaviest spacecraft ISRO has uh, launched. As of now, GSLV Mark III was successful in all of its four missions. Two upcoming missions for safe reentry require developments and changes related to propellant and engine design, component strength and integrity, avionics, and standby system have been in progress. In case of any contingency during the missions, the crew can inspect the launch vehicle and land safely on Earth. Orbital module has two components, crew module and other service module. The Gaganyan crew module is a 5.3-ton autonomous spacecraft designed to launch and safely land a three-member crew. The crew module has a two parachute, one main and another redundant, although a single parachute is adequate for splashdown. During the descent phase of the flight, the parachute would reduce the crew members' module speed from over 216 meter per second to under 11 meter per second. During the descent phase of the flight, the parachute would reduce the crew module speed from over 216 meter per second to under 11 meter per second. Here in image we can see demonstration from 70 kilometer to 60 kilometer. Also as life support and environmental control system are installed in the space capsule, an emergency mission abort capability and a crew escape system are present in the first or second rocket stage. Astronaut entry will occur through a side hatch which will be closed and secured by explosive bolts. The orbital vehicle's nose cone can accommodate docking mechanism for future flights. Service module weighing 2.9 ton is powered by liquid propellant engines. The crew module is connected to the service module and together they form an 8.2 ton orbital module. The service module propulsion system will assist the Gaganyan mission in reaching 400 km in low Earth orbit and remain connected during deorbit burn to re-enter the atmosphere. Part of life support systems, radiators for thermal control and solar panels are housed in the service module. The service module will detach from the spacecraft. Upon re-entry, MON3 and monomethyl hydrogen will be used as oxidizers and fuels in propulsion system. Five engines derived from ISRO's liquid apposimeter will generate 440 Newton thrust and 16 reactions control systems. Thrusters will deliver 100 Newton thrust each. So you can ask what is your capsule recovery experiment. So this is your space capsule recovery experiment, and this is a test experimentally work on how to recover a re-entered capsule from space. It is a 550 kg capsule intended to demonstrate the technology of an orbiting platform for performing experiments in microgravity conditions. After completion of the experiment, the capsule was deorbited and recovered. SRE-1 mission provided valuable experience in navigation, guidance, and control during re-entry phase, hypersonic aerothermodynamic development, reusable thermal protection system, recovery through declaration and flotation, um, uh, besides acquisition of basic technology and for reusable launch vehicles. SRE-1 carried two experiments, an isothermal hearing furnace and a biomimetic experiment. SRE was launched into a 635 kilometer polar SSO in January 2007 as a co-passenger with Cartosat 2 and stayed in orbit for 10 days. Its payloads performed the operations they were intended to. The SRE capsule was deboosted and recovered successfully back on Earth on January 22, 2007. We will now watch a video of the mission.
Over the last 4 decades, ISRO has acquired capability in a number of critical aerospace technologies. India's space program is now poised to enter a new era of testing atmospheric re-entry technologies with the Space Capsule Recovery Experiment. PSLV C7, writing a new chapter in the history of India's space program, blasted off on January 10th, 2007 from Sriharikota.
4, 3, 2, 1, 0, +1, +2.
The vehicle carried 4 satellites on board. Lapan Topsat from Indonesia, Sat-1 from Argentina, ISRO's Cartosat-2, and the most special passenger space capsule recovery experiment, the SRE-1. 56-kilogram Lapan Topsat is a cooperative venture between Technical University of Berlin and the Indonesian space agency Lapan. It is an Earth observation satellite, a technology demonstrator in control system, and carries an experiment for message store and forward system. A 6-kilogram nanosatellite called Sat-1 from Argentina is intended to gain experience in building satellites and operating them. ISRO's Cartosat-2, which weighs 680 kilograms, is 12th in the series of Indian remote sensing satellites and has 1-meter resolution. It is envisaged as an advanced remote sensing satellite carrying on board a single panchromatic camera capable of providing scene-specific spot imageries for cartographic and a host of other applications. The data from the satellite will also find applications in urban and rural infrastructure development and management. SRE-1, Space Capsule Recovery Experiment, is first of its kind in the re-entry technology for ISRO and the country. SRE-1 was placed in its sun-synchronous polar orbit by PSLV C7. A forerunner, SRE is designed with the objectives of mastering the technology of re-entry of space capsules into the Earth's atmosphere after staying in space, provide a platform for microgravity experiments in space, and gain confidence in building reusable launch vehicles. The success of SRE has set the stage for many future missions of India.
The spacecraft recovery module will provide a unique opportunity for the scientific community to experiment under the space environment, especially under the micro-G conditions. So this can be used for a variety of studies, whether it is related to material science or biological science, and that platform can be repetitive use and will be a cost-effective means of conducting such experiments. Of course, the type of inputs what we derive during the re-entry and the splashdown will provide inputs to the design of the manned capsule which we may be taking up for the future.
To make the technology of re-entry of the space capsule possible, SRE was designed, modeled, fabricated, and tested accordingly at Vikram Sarabhai Space Center, VSSC, and ISRO Satellite Center, ISAC, with contributions from Liquid Propulsion Systems Center, LPSC, both at Thiruvananthapuram and Bangalore, and ISRO Inertial Systems Unit, IISU. SRE is a sphere cone flare configuration with a spherical nose of about 0.5 meters radius, base diameter of 2 meters, and 1.6 meters height, comprising of an aerothermal structure, spacecraft platform, deceleration and flotation system, besides the 2 microgravity payloads. The internal structure consists of the spacecraft elements like the Mission Management Unit, MMU, Inertial Measurement Unit, IMU, telemetry and tracking systems, sensor electronics and propulsion systems. The deceleration and flotation system, meant to reduce the velocity of impact and keep the capsule adrift, consists of 3-stage parachute and a float. The external structure of the capsule is made of composite base structure with a thermal protection system made of carbon phenolic at the nose, silica tiles in the forebody, and low-density ablatives at the base of the capsule. The thermal protection system is bonded onto the base structure using high-temperature adhesive. This system is meant to protect the capsule from the severe heating of the order of 250 watts per square centimeter when it travels through the Earth's atmosphere. SRE, weighing 555 kilograms, was placed into a 635-kilometer sun-synchronous polar orbit and stayed there for 12 days.
The space capsule recovery experiment is first of its kind for ISRO. Then we are trying to get an orbiting module back to Earth. This is part of our work effort on low-cost access to space, like reusable launch vehicles, which will actually bring down the cost of having payloads on orbit.
For its first mission, the 2 microgravity payloads performed experiments in the field of material science. First experiment was on the growth of quasi-crystal using isothermal heating furnace, and the other on biomimetic synthesis of nanocrystal through biomineralization. ISRO Telemetry Tracking and Command Network, ISTRAC, was responsible for initial and on-orbit operations of SRE. After its stipulated stay in space and performing the experiments, the capsule, along with its payloads, began its journey back to Earth. SRE was first deorbited in precisely planned maneuvers, starting with the first burn of its thrusters, which placed the capsule into 635 by 490 kilometers daily repeating elliptical orbit prior to re-entry. A number of experts from all ISRO centers converged at ISTRAC Control Center at Bangalore to command the spacecraft and carry out all the precise operations for the successful on-orbit and re-entry phases of SRE. The re-entry of the capsule starts with a deboost operation by the firing of all thrusters and further reorientation of the capsule, moving it to the edge of the Earth's atmosphere. The deboost operation lasts for 535 seconds, thereby reducing the velocity of the capsule. With the completion of the deboost operation, the re-entry of the capsule commences. The angle of flight path of the capsule into atmosphere interface at 100 kilometers altitude has to be very precise for re-entry to happen. The presence of plasma envelope leads to a communication blackout, which lasts till about 40 kilometers. Traveling at a velocity of 8 kilometers per second, entry of the space capsule into the Earth's atmosphere generates tremendous amount of heat caused by skin friction. The temperature experienced is in the order of 2000 degrees centigrade at the nose cap and 1400 degrees centigrade on the silica tile. During this phase, the thermal protection system of the capsule safeguards the internal structure. The heat generated during the re-entry is proportional to the initial total energy, both kinetic and potential. The thermal protection system's design is a trade-off between the allowed heating rates that the TPS materials can withstand and the total heat load on the capsule. This design works on two principles of radiative cooling and ablative cooling. The silica tiles, an excellent insulator capable of withstanding high thermal shocks, works on radiative cooling mechanism. The carbon phenolic nose cap, which sublimes under entry heat load and keeps the underlying structure within the operating limits, works on ablative cooling principle. About 5 kilometers above the sea level, three parachutes in SRE open up sequentially at prescribed altitudes. The parachute system is meant to reduce the touchdown velocity approximately from 100 meters per second to 12 meters per second at the final touchdown. With touchdown, the parachute gets detached from the capsule and flies away. Subsequently, a float gets inflated that keeps SRE adrift. The SRE recovery operations from the sea are coordinated by Satish Dhawan Space Center SDSC Char. After 12 days staying in orbit, SRE-1 splashed down in the Bay of Bengal, about 140 kilometers east of Sriharikota coast. The probable elliptical impact zone of 30 by 5 kilometers in the Bay of Bengal was earmarked and cordoned off from the safety point of view. A UHF homing device, combined with a sea marker dye emitted from the capsule, which leaves a trail in the sea, makes it easier to track and locate. Airborne telemetry, shipborne telemetry, Indian Coast Guard ship Sarang, and Chetak helicopter from Sarang are stationed beyond the 50 by 15 kilometers stay-out zone. The helicopter responsible to locate SRE also conducts safety tests. On confirmation, a diver enters the seawaters to attach an additional buoy to the capsule. A team of divers from the Indian Coast Guard takes over and connects the flotation toroid. Before recovery, the condition of the capsule submerged under seawater is photographed. After this, the capsule is towed to the ship and recovered. The recovered capsule, along with its payloads, is sent to ISRO centers for further analysis and study. Space Capsule Recovery Experiment is a modest beginning, which will provide a low-cost platform to conduct microgravity experiments and enable the return of specimen from space back to Earth.
So, crew module was the payload in GSLV Mark III X Care Mason. CARE is the acronym for Crew Module Atmospheric Re-Entry Experiment. The mission was used as a platform to test the re-entry technologies envisaged for the crew module, including validating the parachute-based deceleration system's performance. CARE enhanced the understanding of blunt body re-entry aerothermodynamics and parachute deployment in a cluster configuration. The external configuration of the crew module to be flight tested in GSLV Mark III is the same as that of crewed flight. So this video shows how the module was recovered. Objective of this module are demonstration of re-entry flight of crew module, end-to-end parachute system validation, demonstration of apex cover separation, demonstration of parachute deployment. The crew module was separated from the launch vehicle at an altitude of 126 km, re-entered Earth's atmosphere at about 80 km, and descended further in ballistic mode. Beyond 80 km, crew module followed an uncontrolled re-entry trajectory and impacted at sea about 180 km from Andaman and Nicobar Island, from where the Indian Coast Guard recovered it. On July 5, 2018, the first in a series of tests to qualify a crew escape system, which is a critical technology relevant for human space flight, the crew escape system is an emergency escape measure designed to quickly pull the crew module along with the astronauts to a safe distance from the launch vehicle in the event of a launch abort. The first test pad abort test demonstrated the safe recovery of the crew module in case of any exigency at the launch pad. After a smooth countdown of 5 hours, the crew escape system, along with the simulated crew module, with a mass of 12.6 tons, lifted off at 7 a.m. Indian Standard Time at the opening of the launch window from its launch pad at Satish Dhawan Space Center, Sriharikota. The test was over in 259 seconds, during which the crew escape system and the crew module soared skyward, then arced out over the Bay of Bengal and floated back to the earth under its parachutes about 2.9 km from Sriharikota. The crew module reached an altitude of nearly 2.7 kilometers under the power of its seven specifically designed quick acting solid motors to take away the crew module to a safe distance without exceeding the safe G levels. Nearly 300 sensors recorded various mission performance parameters during the test flight. Three recovery boats were exercised to retrieve the module as part of the recovery protocol. So you can see the demonstration of that crew escape system flight test. ISRO is developing it for the first time. The ECLSS, that is Environmental Control Life Support System, to maintain the cabin pressure within limits. Oxygen supply, filters for cleanliness, pressure control, humidity control, gas sensors, personal hygiene, and fire systems are in present. A thermal and humidity control system to keep the temperature inside CM within the acceptable limits, comfortable for the crew, and air revitalization system for removing carbon dioxide and odor from the cabin. The Human Space Flight Center was constituted in ISRO in January 2019 to implement the Human Space Flight Program vision. The Gaganyan project is being executed through all ISRO centers with HSFC in the lead role. For effective interagency coordination of activities and addressing the criticality, a national level Gaganyan Advisory Council comprising of experts from various government departments, national institutions, and industries was set up. The first meeting of Gaganyan Advisory Council was held on June 8, 2019. For some of the critical technologies such as space food, space crew health monitoring and emergency survival kit, radiation measurement and protection and parachutes for the safe recovery of the crew module, ISRO and HSFC signed MOUs with various DRDO's labs and other organizations or institutions such as Aerial Delivery Research and Development Establishment, Defense Food Research Laboratory, Defense Bioengineering and Electromedical Laboratory, Defense Laboratory Jodhpur, Center for Fire, Explosives and Environmental Study, Safety, Institute of Physiology and Allied Sciences, Center for Military Airworthiness and Certification, Institute of Nuclear Medicine and Allied Sciences. The Indian Air Force and Institute of Aerospace Medicine are identified for crew selection and training. The first phase of crew selection and training has been completed in Russia, and now the crew is undergoing functional expertise training within ISRO. The following are some of the institutes that are developing the scientific payloads for carrying out various experiments: Indian Institute of Space Science and Technology, University of Agriculture Sciences Dharwad, Tata Institute of Fundamental Research, IIT Patna, Indian Institute of Chemical Technology, Jawaharlal Nehru Center for Advanced Scientific Research. A total of 5 experiments will be performed, of which 2 will be biological experiments conducted by IISD, UASD, and TIFR. The experiments will examine kidney stone formation and sirtuin-1 gene marker effects in Drosophila melanogaster, common name fruit fly. IIT Patna will develop a heat sink that can handle very high heat fluxes. IICT will study crystallization processes, and JNCASR will evaluate fluid mixing characteristics. Once the astronauts return to the Earth, they are taken for rehabilitation, where astronauts will stay in isolation and take time to recover from the effects of space travel, that is, changes into the environment of microgravity in space to the gravitational force on Earth. Also, during the rehabilitation, the experts in space medicine will study the health of astronauts to see if they are affected due to weightlessness, space radiation, gravitational force, etc., and provide the consultation. The effects of microgravity will be very minimal for short trips up to 1 week compared to year-long missions. But the study will help to make the technology ready for future missions. So now we will we can think of what is a humanoid robot. So half humanoid with anthropogenic proportions with two arms, lead uh, lead two arms, head and torso to mimic crew activity inside crew modules is flying in first unmanned flight. It has a capability to voice command reception, speech context, based facial expression, visual monitoring, adjustable postures, mainly intended for data collection and limited operations. This ensure crew survival in case of pressurization during an off-nominal situation, protect the crew from decompression sickness, hypoxia, and fatal injuries due to exposure to extremely low pressure. And depressurization of suit could be due to hull breach, accidental slow depressurization, over oxidization, smoke or fire, high carbon dioxide bubble. It has two modules, 2 modes. Zero point 0.4 mode is nominal mode and 0.27 mode easy mode for better suit mobility. Under completion, India would become the fourth nation in the world to conduct self managed human space flight after the Soviet Union or Russia, the United States, and China. In the long run, ISRO expects to construct a space station and beyond. There are both tangible and intangible benefits associated with human space flight. The nation benefits from this project by advancing towards a sustainable and affordable human as well as the robotic program to explore the solar system and beyond. As a result of the mission, advanced technologies will be developed for human space exploration, sample return missions, and scientific explorations. We will be able to collaborate with global space station development and conduct scientific experiments of national interest. In addition, advanced research and development activities offer enormous opportunities for employment generation and human resource development. Lastly, it will inspire and excite the nation's youth like you all and encourage them to pursue careers in science and technology. So thank you so much. You can, if you have any queries, you can write to us for the any doubts regarding your Gaganyan mission. Thank you so much.